Throughout his long career, Sony co-founder Masaru Ibuka presided over many special devices. But the one he was most proud of? A color TV of all things. But no product better explains Sony's engineering prowess and tenacity. It took Sony nearly 8 years to bring it to the market, but when it came out, no one else's color TV could compare. In this video, we look at Sony's breakthrough color TV, the Trinitron. Before we begin, I want to mention that this video is part of a series on the histories of the color television, done in collaboration with our friends at IEEE Spectrum. More later. Now on with the show. Inside Sony's beating heart are its two co-founders, Masaru Ibuka, the company's whirlwind engineer, somewhat naive, playful, and guileless in the real world, but also tenacious, relentlessly driven towards excellence, and an incredibly motivating engineering leader. And then there is Akio Morita, 13 years younger than Ibuka, scion of a wealthy sake family, though, funny enough, he does not drink. Morita was Sony's charismatic business leader and spokesman. Pragmatic and to the point, Morita gets things done and done fast. And though his family was Sony's single biggest shareholder, Morita looked up to Ibuka. Morita's guiding principle was to ensure that Ibuka and his team got the money to produce their projects. Ibuka and Morita worked together for 40 years and almost never argued. They were perfectly suited for each other in achieving their dreams of bringing consumer electronics to ordinary people. They started off producing professional audio equipment like the G-Type, Japan's first commercially available tape recorder. They then early on licensed the transistor from Western Electric and harnessed its power. Sony's team of cracked engineers then used it to produce popular consumer devices like the breakthrough TR-55 and TR-63 pocket radios. Rising competition in transistor radios, however, motivated the company to research new categories. The obvious next candidate for transistorization was the black and white television, which were then getting extremely popular. These worked with an electron gun pointed at the screen. The inside of the screen is painted with a glowing material, or phosphor. During operation, the gun fires electrons at the screen, and when those electrons hit the phosphor gets energized and releases light. To put images onto the screen, you use energy to deflect the beam. Because you need a good amount of energy to do this, and things can get rather hot inside the television, normal germanium power transistors are not sufficient. You needed something stronger. Namely, you needed silicon. Its higher melting point lets it handle these higher temperatures. In 1956, Ibuka and his top technology R&D guy, Kazuo Iwama, attended a Bell Labs seminar. The people there claimed that silicon would be the future. Ibuka echoed this sentiment when he predicted that, quote, "This will be the age of silicon," end quote. Silicon transistors did already exist then, but they were small, more suitable for handling signals rather than power currents. Nevertheless, Ibuka assigned a team to produce these silicon power transistors from the ground up. It was an interesting time in semiconductor technology. Pure silicon then cost more than its weight in gold. Sony had to buy 20mm crystals from France. Photolithography had not yet been invented, so to apply the pattern design, the Sony team had to use oxide and mesa masking. This involved selectively applying and etching away layers on top of the raw silicon. Sony's first product with silicon transistors, released in 1960, was the TV-8-301. Despite being transistorized, it was small, fragile, and did not sell well. So what next? At the time, the American market seemed to prefer big screen TVs. The obvious thing to do then would be to follow the crowd and produce those big screen TVs. But Sony had hit the limit of their silicon power transistors. Existing impurities in the silicon cause excess power leakage. The larger the chip got, the worse the leakage was. Since the power transistor cannot get any bigger, the transistorized TV could not have a screen much larger than 5 or 8 inches. American marketing consultants very strongly insisted that a TV with such a small screen would fail in the market, but Ibuka pushed to turn this supposed weakness into a strength and lean into the TV's small size. So they did, Morita, then spending time in Sony America's headquarters in New York City, began preparing a marketing campaign for what was called the, quote, micro TV, end quote. He spent long nights sitting in front of the TV, studying commercials. He snagged Volkswagen's advertising agency in the US, somehow convincing them that the Sony name will soon be a big one. And the Sony salespeople worked harder than they ever before thought was possible. One Japanese salesperson recalls, "We had never distributed before in our lives. We didn't even know how to price our products. I had been in the Japanese army and knew what it meant to go all out, even to risk your life. But I worked harder in New York." The efforts paid off. The 5303W Micro TV sold very well. 50 plus years later, Redditors are playing Call of Duty on it. As soon as Sony's engineers finished engineering the TV, Ibuka started talking about turning to the color TV. This one was a bit tricky. In the 1940s, a team at CBS patented the field sequential system for color television. It involved mechanically rotating a set of red, blue, and green filters at 1,400 revolutions per minute in front of the camera. This creates red, blue, and green images. A special color TV would then show the red, blue, and green images one after the other sequentially. It displays this so fast that the human brain perceives it as a single full-color image. The concept behind this CBS system is reminiscent of an earlier work by John Logie Baird in 1928, but it produced a far better image. The catch is that to avoid a noticeable flicker, we needed a high refresh rate, which would have meant sending 3 times the number of images as black and white broadcasts. This was unacceptable, so the CBS engineers instead slightly reduced the frame rate as well as the size of the frames themselves, creating a rather small image. These modifications made the CBS setup incompatible with existing black and white systems. At the time, RCA had a sizable investment in this black and white ecosystem. They risked losing it all if the US adopted the CBS color system. So, in a 6-month crash program starting September 1949, RCA produced the shadow mask tube as a credible alternative. In this system, you have 3 electron guns, one for each primary color, red, green, and blue, placed in the back of the television. The guns fire converging beams towards the eponymous shadow mask, a thin metal sheet with tiny holes drilled into them. The shadow mask is positioned right in front of a screen coated on the inner side with red, blue, and green phosphors set in pixels. The electron guns are positioned in relation to the shadow mask such that the right electron beam passes through the mask's holes to hit the right phosphor. So, electrons from the green beam only hit the green phosphors on the screen, making it glow. The red, green, and blue phosphors glowing next to each other fools our primitive carbon-based meat brains into thinking there is color. It wasn't super bright, but it was compatible with existing black and white systems, and that was what mattered. Unlike the black and white TV, which caught lightning in a bottle as soon as it hit the market, color TV adoption started off slowly. 6 years after the release of the first RCA color television, US consumers bought just one color set for 50 black and whites. The situation was even worse in Japan. Just 300 of 9 million sets sold that year were color sets. At first, you could blame this on content availability. But in 1962, the US's National Broadcasting Company, or NBC, started producing 2/3 of their nighttime programming in color, kicking off new growth in color TV content. Thus, one must also blame the shadow mask tubes. First of all, the screen was not particularly bright. 85% of the guns' electrons hit the mask, not the screen. You can do brighter phosphors or more powerful guns, but 15% efficiency will always look pretty bad on the screen. More importantly, the need for 3 separate electron guns converging towards a single point meant extra manufacturing work and higher cost. Each TV set had to be manually tuned by a skilled and trained human worker. The setup was also vulnerable to external magnetic fields from nearby appliances or even the Earth itself. Any such interference would mess with the 3 beams' aim, creating these annoying colored patches. This issue would not be resolved for years. This is all in addition to the difficult challenges of making the shadow mask itself, produced using a combination of chemical, mechanical, and photographic techniques. You can see why it was not super ideal. RCA made its shadow mask tube system widely available for licensing, and despite its warts, many companies licensed it. Sony considered licensing the system too. They were seemingly behind in this market, and an RCA license would have been the fastest way to get a Sony color TV onto the shelves. But in a moment of cheekiness, Ibuka thought it would be, quote, no fun in merely copying the market leader. But if not RCA's tech, then what? In 1961, Ibuka and Morita attended a trade show sponsored by the IEEE in New York, and there on the show floor, they saw the chromatron. The chromatron has a fascinating history. It was invented in 1951 by Dr. Ernest Lawrence. Lawrence is a physics Nobel winner and also invented the cyclotron. He was the guy that Josh Hartnett portrayed in the movie Oppenheimer. IEEE Spectrum has a fascinating video on the history of Dr. Lawrence's efforts inventing the chromatron in a video on their own YouTube channel. Go watch that one right after this one. So Morita sees a crowd gathering around the sharpest and brightest color screen he has ever seen. He is so impressed that he immediately calls the technology's owner, a subsidiary of the movie studio Paramount Pictures, and gets a technical license. A few months later, Sony sends a young Argentina-born Japanese physicist named Senri Miyaoka to learn the chromatron's technology from the licensor. Miyaoka recalled going to a dark, windowless basement lab and meeting a team of 10 glum, very frustrated Americans. As the Americans explained the chromatron's technology to him, one even thanked him for releasing them from such a thankless task. Miyaoka sensed that Sony had gotten itself involved in something formidable. If the RCA Shadow Mask's tube system's main headache was the intricately aligned convergence of 3 electron guns, then replacing the 3 guns with 1 fixes that. But as they say, out of the frying pan and into the fire, this thing is insane. The chromatron works similarly to the shadow mask tube in that it fires electrons at phosphors on the inside of a glass screen, but with some changes. First, the 3-gun arrangement is replaced with a single gun. The screen phosphors are no longer arranged in pixels, but instead in parallel vertical stripes, green stripes, blue stripes, and red stripes. The gun is loaded with sequential information of the color image, green, blue, red data, and then fires. To trick the human brain into seeing a full color image, we need the right color information from the gun hitting the right color phosphor stripe, red info to red stripe. Does that make sense? So how do we achieve this? The shadow mask tube used the shadow mask to keep unwanted electrons from reaching the phosphors on the screen. Chromatron did this differently. It had a grill of charged wires running vertically up and down positioned just inside the screen. These are color-selecting wires, and there are up to 400 of them. They activate at just the right time and deflect unwanted electrons such that only the red signal information hits the red phosphor stripes, and so on for the other colors. What a high wire act. Sony spun up a brand new factory in Tokyo to build the chromatron, but mass production dragged on and on. One big challenge was synchronizing the electron beam and the activation/deactivation of the metal lines in the grill. I've seen it described as something like swinging your arms back and forth and snapping your fingers at the apex of every arm swing. When it worked beautifully. But when it did not work, and that happened quite often, you got these sickening color variations. In September 1964, Sony had a 17-inch chromatron prototype and put it in the Sony showrooms to build hype and air horns. But behind the scenes, the factory was struggling. With 27 vacuum tubes and delicate wires spaced less than a millimeter apart from one another, it was 10 times more complicated to produce than a standard shadow mask tube color TV. For every 1,000 TV sets that Sony made, just 2 or 3 worked as intended. If the grid moved, the misalignment would cause people's faces to turn green, like as if they were the Hulk. Ibuka, though, refused to back down from mass production, saying that if one set worked, then improvement can be achieved. And to be fair, he said the same thing before, when Sony was struggling to ramp up its transistors for its first transistor radio, and that worked out. But not this time. In 1965, the Sony team decided that the one-gun method that Dr. Lawrence originally used for the chromatron could not be used. The cost of the color-switching grill was just too high. So they switched to a three-gun method, one for each color like as before. This brought back the gun alignment issue. A tiny misalignment can cause more color variations, but it loosened the tolerances between the vertical wires, so it was easier to make. So, in May 1965, they released a 19-inch chromatron to the Japan market, eventually selling 13,000 sets there. Each set sold for 198,000 yen, or $550, but cost 400,000 yen, or $1,111, to make. Not to mention all the defects plaguing buyers. Sony had to grant a lifetime warranty, and boy was it used. Such economics are not favorable, yet Ibuka again refused to shut it down and switched to the RCA shadow mask. In fact, he doubled down and made the chromatron Sony's single highest priority, with 150 people working on the team. By 1966, the shadow mask tube system was fully mature in the market and color TVs were going mainstream. Sony's distributors and dealers urged the company to bring a color TV to the US or see their position there come increasingly at risk. Every Chromatron TV set Sony sold, though, lost them money, not to mention the $700,000 in development costs the company was spending each year on fixing issues. For the first time, people sensed tension between the two legendary co-founders, Morita wanting to cut their losses, but Ibuka digging in. No one ever saw them actually arguing, but the strain was palpable. During the worst of it, accountants and business planners started appearing at the Chromatron engineering brainstorming sessions. They said nothing, but everyone in the sessions knew that they were reporting back to quote-unquote Morita's people. Then there was the time Morita himself angrily berated the Chromatron team for exploiting Ibuka's commitment to the Chromatron so to explore, quote, curiosities in the problem-solving process, end quote, without actually solving said problems. Despite this, behind the scenes, Morita worked with the Japan Development Bank for a $2 million loan to continue funding the R&D effort. Finally, in 1966, Ibuka agreed to dissolve the team and adopt the shadow mask tube if a viable alternative cannot be discovered by the end of the year. He agreed to personally lead them, feeling the lost preceding 5 years to be all his fault. The color TV team split up, exploring varying approaches in parallel. Ibuka went between them, asking questions, offering encouragement, and sometimes even directly participating in the experiments. In 1966, General Electric released their Portacolor TV color set. It was also a shadow mask tube, but with a twist. It had a single electron gun equipped with 3 cathodes arranged in a straight line, creating 3 beams. By contrast, the Chromatron arranged its 3 guns/3 beams in a triangle or delta formation. One of the team's managers, Susumu Yoshida, went to General Electric to review the idea and maybe license it. But Yoshida didn't think that the Portacolor was bright enough. It still used a shadow mask, but he was intrigued by the 3-cathode 1-gun setup and how it might work when paired with the Chromatron's grill. So he suggested this idea to his subordinate, Senri Miyaoka, the guy who went to the American dungeon to first learn the Chromatron process. Miyaoka then rigged it up by strapping 2 cathodes to the sides of a standard black and white electron gun. He was surprised to find that this arrangement created a bright, albeit blurry, picture. Miyaoka did a few more experiments and then wrote it down into a report. Ibuka read that report and summoned Miyaoka to discuss just before the latter had to go to his weekly orchestra practice. In a hurry to end the conversation, Miyaoka said, quote, yes, this can work in a commercial system, end quote, and then rushed out the meeting to go play the cello. The following Monday, Ibuka reoriented his 7,000-person company towards this one thing. He became obsessed with it, dropping whatever he was doing at the time whenever someone came to him with a question about it. Sometimes he even wandered off with them to the lab afterwards to see. The Trinitron gun was completed by February of 1967, and the prototype completed in November 1967. It is a beautiful piece of work. On one end, you have a single electron gun with the 3 RGB cathodes arranged in the horizontal line. At the other end, you have, as usual, the screen with the 3 color types of phosphors painted on the inside. The gun uses its 3 cathodes to fire 3 electron beams. They then converge towards a common point, crossing each other at the center of a large electron lens. This crossing, or convergence, is also the origin of the name, Trinitron. After crossing over, they expand outwards again, like as if from a single point. Deflection plates are then used to focus and direct the beams towards the right phosphor stripe inside the screen. Instead of a shadow mask in front of the screen, the Trinitron has an aperture grille. It is comprised of etched vertical metal wires, one for each color. The grille does the same thing as the shadow mask, separating the color beams to ensure that the right beam hits the right phosphors. But the vertical lines allow more electrons to pass through, which means a brighter picture. One can argue that the aperture grille is as big a breakthrough for the Trinitron as the electron gun. It certainly brought its share of engineering challenges. The electron bombardment heated up the metal, causing it to expand or shrink, and that gave Ibuka and everyone else involved a big headache. Sony announced the Trinitron on April 15, 1968, 4 days after Ibuka's 60th birthday. Ibuka hosted the press conference himself in Tokyo with 10 prototypes on the stage. Yoshida had earlier estimated that it would take about a year to ramp up production, so he must have had a mini heart attack when he heard Ibuka tell the world that Sony would offer 10,000 Trinitrons for the public by October. Morita said the same thing later in New York. The team protested, and Ibuka told them to study the American Manhattan Project for inspiration, and to Yoshida he said, "I will never do this to you again, so please indulge me this once." Yoshida had to be the bad guy to turn the 10 prototypes into a commercial product. His team started calling him Shogun Yoshida due to his ferocity in running the team towards the finish line. Sony dealers from the start wanted a Trinitron with a 17-inch screen size, but to speed up the commercialization process, Sony opted to first bring out a 12-inch screen version of the Trinitron. Competitors later claimed the set's brightness and quality was because its smaller size. Not true. The smaller screen was just to get it out faster. 6 grueling months later, the team of 100-plus engineers and scientists started rolling the first sets off the Tokyo factory line, the culmination of an 8-year and $12 million development odyssey. The Trinitron broke RCA's years-long virtual monopoly on color TVs. It was a true game changer. On the basis of its far brighter screen and simpler production process, the Trinitron quickly won the small color TV market in Japan. By March 1969, they were selling 10,000 sets each month, ramping up to 20,000 a few months later. They could not keep up with demand, and factories had to be spun up in San Diego and the United Kingdom. From 1968 to 1998, Sony sold 180 million Trinitrons. Sony finally ended the Trinitron line in the 2000s when LCDs and other semiconductor displays finally took over. Remarkably, the system remained largely the same for some 20 years after its introduction. The Trinitron was one of the last Sony products that Ibuka directly oversaw. Afterwards, he transitioned out of day-to-day operations and into more personal pursuits like youth education. He passed away in 1997 at age 89. What a thing to end on. Alright everyone, that's it for tonight. Thanks for watching. And make sure to watch the companion videos on the IEEE Spectrum YouTube channel that go along with this one. But anyway, subscribe to the channel, sign up for the newsletter, and I'll see you guys next time.